Thank you. And good evening, Bromsgrove, once again. Yes, it's not rocket science, and the subtitle there, well actually, yeah, it is rocket science, but it's not that hard as long as you skip the maths.
What do you do?
Well, I don't mean to boast, but I'm a brain surgeon.
Brain surgery? Not exactly rocket science, is it?
So I am not talking about how you would go about building a Saturn V. If you want to build a Saturn V, well, you can build one in your back garden if you get the Haynes manual that tells you how to put it together, or you can go for an Airfix model, or like this one, kindly donated by Sue and Rob this evening, we can go for a Lego model. So I'm not talking about how you build a rocket. This evening, I'm talking about what rockets actually do, in other words, what rocket science is, talking about orbits, Kepler, Newton, etc., how we go between orbits in the solar system, in other words, how we get from A to B if we want to explore the solar system, and those mysterious parking places in the solar system that we call Lagrange points. How is it that we can send the James Webb Space Telescope to a point in space and park it there? So firstly, rocket science. What does a rocket actually do? Perhaps this audience already knows, but if you ask the man in the street, most people will say the purpose of a rocket is to lift stuff above the atmosphere into space. Well, yes and no. That's not the prime function of a rocket. The prime function of a rocket is actually to go sideways. Because if you go to the height of, for instance, the International Space Station or the Hubble Space Telescope, you are still inside the atmosphere. Yes, the air is very thin up there, but technically you're still within the Earth's atmosphere. To put an object into Earth orbit, what you absolutely need is not actually height, it's horizontal speed. Yes, getting as high as possible is a good idea because you don't really want too much air resistance, but technically height is not a prerequisite for going into orbit. Ever since Newton, we've known that. Back when the Principia was put together in 1686, Newton said, if you fire a cannonball sideways, if it goes slowly, it'll simply drop back to Earth. But if you fire a cannonball fast enough, it'll actually go into orbit around the Earth. That's why horizontal speed is key, and we've known that for hundreds of years. Let's remind ourselves of how this beastie on the left actually works. Yes, rockets go up vertically to start with. But actually, it's not long before they start to tilt over. That's not an illusion of the way the camera is taking the images. The rocket is genuinely tilting over in order to increase its horizontal velocity rather than its vertical velocity. If you don't bother about the horizontal, then what does your rocket do? Well, it goes vertically up, as in Blue Origin, for instance, and once you cut the engine, you come vertically back down again. If you don't have horizontal velocity, you don't go into orbit, you just reach a particular height, which may or may not be space, depending on how you define it, and then you come straight down again. So in the case of New Shepard, it went up to something like 100 kilometers, and 10 minutes later, it was back down on the ground, not far from where it launched. Horizontal velocity is key. So let's think about orbits. And we're used to the idea of thinking about planets in orbit around the sun, moons in orbit around planets. But perhaps you're not really familiar with the fact that there is a very precise definition for an orbit, and that is the path of an object that's affected only by gravity. In other words, whilst a rocket engine is firing, then technically the rocket is not in any particular orbit. It is subject to gravity and the forces of the rocket engine. Only when the engines are cut and the object is coasting do we actually define the path of the object as being an orbit. So we're used to the idea that, yeah, we know what orbits are. We know that planets go around the sun and moons go around planets, etc. So Kepler observed the motion of the planets and decided that looks like most of the planets seem to orbit in ellipses, sometimes very close to circles, but generally in ellipses. And at roughly the same time, Newton came along with the explanation as to why planets orbit in ellipses, because of the universal law of gravitation. So Newton found that by dealing with the mathematics of being pulled towards the sun by the sun's gravity, you can show that objects that are in orbits will follow so-called conic sections. In other words, the geometric shapes that you get if you take a cone and then you slice that cone horizontally, you get a circle. If you slice the cone at a slight angle, you get an ellipse. If you slice the cone parallel to one of its sides, the shape is a parabola. If you slice the cone at a more vertical angle, you'll get a hyperbola. So these four shapes are all shapes defined by cones cut at different angles, hence the term conic sections. And when we look at them all plotted here, around the same central object, let's just imagine this is the sun, for instance, we see we have circles, ellipses, parabola, and hyperbola. And the curves that define the orbits around a central object like the sun, they're the same curves, the same shapes that define how we can focus light. We can focus light with spherical or elliptical or parabolic or hyperbolic mirrors. That's how we make reflecting telescopes. And the reason that orbits are the same shape as telescope mirrors are effectively because the maths doesn't sound like it's the same, but underneath it all, the maths is the same. So you end up with the same set of solutions. It's been known for a long time that planets follow elliptical orbits. If we look at objects that are coming far out in the solar system, for instance, way out in the Oort cloud, still hypothetical, but we believe comets coming from a great distance are coming from a huge reservoir called the Oort cloud, a huge distance, maybe a light year or so away from the sun. That's almost infinity. Anything dropping into the solar system from that distance follows a parabolic path. And anything that comes into the solar system at speed with a velocity such that it has an escape velocity, well, that would have a hyperbolic path. So we can differentiate between circular and elliptical and parabolic and hyperbolic orbits. We know a bit about hyperbolic orbits because fairly recently we've seen a few of these objects. For instance, in 2017, this rock came into the solar system and it followed a path that we could trace out, and that path was hyperbolic. In other words, it matched that particular shape on the cone. Also, you don't actually need to trace out the whole path. All you really need to do is work out its velocity at some point or another and compare that with the escape velocity of the solar system, which we can calculate because we know the pull of gravity from the sun. If the object is traveling faster than the escape velocity, then it must have come into the solar system at some speed, and it will leave the solar system at that same speed. In other words, it hasn't simply fallen in from the Oort cloud. So we know we've already seen a few interstellar interlopers coming in on hyperbolic orbits. Let's just think a little bit about orbital mechanics, because that's sort of fairly key to what I'm talking about this evening. Let's take a couple of hypothetical planets, a green planet and a red planet orbiting the sun. The green planet is closer to the sun, so it feels a stronger gravitational pull, and so the planet moves faster to stay in orbit. In other words, it has a shorter year, if we're taking year to mean the length of time it takes to go around the sun. The red planet is further from the sun, so it feels a weaker gravitational pull, and so the planet moves more slowly to stay in orbit. It's not simply that the red planet has got further to go on its racetrack, it is actually moving more slowly in terms of kilometers per second. Let's just run that again so we can see it. This is key to pretty much everything I'm saying this evening. If you're closer to the sun, you're feeling a stronger gravitational force, you move faster. If you're further from the sun, you feel a weaker gravitational force, you move more slowly. So let's see how that affects real things. This is a very busy slide, I realize that, but it's an animation that reminds us that, for instance, the space station and the Hubble Space Telescope, only a few hundred kilometers from the surface of the Earth, they're going around the Earth in about 90 minutes or so. GPS satellites are much further out. They take about 12 hours to go around the Earth. And further out still, in a geostationary orbit, we have objects that are going around in 24 hours. The further you are from Earth, the longer your year, or the longer it takes to do one orbit. It doesn't really matter whether we're talking planets around the sun or artificial satellites around the Earth. It's still the same fundamental principles: stronger gravity, faster motion. So Hubble and the space station orbit in 90 minutes, everything else much more slowly. It may come as a surprise to realize that despite all of the work of Newton and every clever scientist since, we find that it's easy to work out a problem of one object orbiting around another, but it's actually insoluble to work out three objects orbiting around each other. That sounds so trivial. If we can do it for two, surely we can do it for three. Turns out we have no understanding of how we can analytically solve the equations of motion that tell us how three bodies move relative to each other. So in practice, that means if we want to actually work out how objects are moving, we calculate how one object is moving relative to another by ignoring everything else and then making corrections or approximations. If we were to run a simulation of how three objects move around each other, it's insoluble except for very specific circumstances. In this particular case, you think, oh, this is very neat and tidy. They're all moving in ellipses around each other. That's great. But we run this simulation for a little bit longer and, oh, actually, they weren't in ellipses. They're actually, wow, yeah, that is so far removed from conic sections. Clearly, it doesn't work. We can do simulations. We can do numerical approximations. We can work out things and make corrections, but we can't actually work out analytically the solution for two objects orbiting around a third, for instance. A bit of a surprise, but that is still a limitation of how we deal with orbital mechanics. So how do we get from one place to another in the solar system? We, of course, are sitting on Earth at the moment, and Earth is going around the sun. If we want to go to another planet orbiting the sun, how do we do that? Well, here's an example taken from quite a few years ago now. If we want to leave Earth, Earth in blue, Mars in green, and purple is our spacecraft, we can leave Earth and arrive at Mars when Mars is on the other side of the solar system. That's a little bit counterintuitive, but remember we left Earth down there and we arrive at Mars. Notice that Mars is catching us up. If we run that particular simulation again, we leave Earth down here. It takes about 8 to 9 months for us to go from Earth on this side to Mars on the other side of the solar system. This is the most fuel-efficient way of getting from one point to another. Notice that we're ahead of Mars and Mars is catching us up, which means at that particular point we're moving more slowly than Mars. So that tells us what we need to do in order to actually go into Mars orbit, or for instance to land on Mars. That's way too complicated. Let's get rid of that. Let's dim that down a bit and boil it down to its basics. If we have Earth in orbit around the sun and we have Mars in orbit around the sun, quite definitely not to scale. I've deliberately made the Mars orbit bigger just so that we can see what's going on a little more clearly. We are going to leave Earth when it's on this side of the solar system and arrive at Mars when it's on the opposite side of the solar system. And the orbit we take is that blue line, that blue ellipse. If I take away Earth and Mars temporarily, we are going to be transferring from Earth orbit to Mars orbit in this ellipse. It's called the Hohmann transfer. Perhaps you remember that if you've ever seen The Martian. They kept referring to the next Hohmann transfer, the next Hohmann window. So it's an ellipse, and the closest part of the ellipse to the sun is the same as the Earth-Sun distance, and the greatest distance from that ellipse to the sun is the same as the Mars-Sun distance. So you might say, well, this is fair enough. So how do we actually get from the Earth orbit into the blue orbit, the Hohmann transfer? Well, we need to accelerate. We need to give a little bit of a kick. That's where our rocket engines come in. We need to go faster than the Earth is traveling. We need to increase our velocity by approximately 3 kilometers per second. So we need a change of velocity, or as the rocket scientists call it, we need a delta V. It doesn't really matter what the acceleration is. In other words, it doesn't matter whether you gain that velocity over 1 second, or 10 seconds, or 100 seconds, or 1,000 seconds. How fast you get there, how quickly you accelerate, doesn't really matter. What matters is you need to be going faster by about 3 kilometers per second by the time you've finished your rocket burn. So if you've got a really powerful rocket, you only fire it for a short time. If you've only got a very weak rocket, then perhaps you have to fire it for a little bit longer. So we need a rocket burn that gives us a change of velocity, a delta V, of 3 kilometers a second, and that takes us out of Earth orbit into the blue Hohmann transfer. And then when we arrive at Mars, remember that previous animation? Mars was catching up the spacecraft. In other words, the spacecraft is going too slow. So if we want to rendezvous with Mars, we need to accelerate to catch up with Mars's velocity. We need another delta V. We need another rocket burn, this time roughly 2 kilometers per second of more velocity, in order to catch up with Mars if we then wanted to go into orbit or land on Mars. So we need to fire the rockets when we leave Earth. We need to fire the rockets again when we get to Mars. That's, if you like, a standard way of getting from one orbit to another. You might look at that and say, well, if we need an extra kick when we get to Mars, I presume that means if we spend a little while on the Hohmann transfer to get to Mars, and when we get there we decide not to land, presumably all we have to do is to avoid firing the engines and we'll just continue on the blue curve, because we won't catch up with Mars to rendezvous. We'll just stay a little bit too slow and we'll fall back towards Earth orbit on the blue curve and we'll be home again. Well, no. It takes a year for the Earth to go around the sun. It takes about 2 years for Mars to go around the sun. How long does it take to do the complete Hohmann transfer there and back? In between 1 and 2 years, about 1.5 years. So if you leave Earth and then you come back here 1.5 years later, where's the Earth? The Earth takes a year to go around the sun. So when you're back here, the Earth has already done 1 orbit and half an orbit, and the Earth is now on the other side of the sun. So if you go to Mars, decide not to land and come straight back again, Earth is not where you left it. And that's a real problem for a Mars mission. You can't simply take a shortcut. Mars and Earth have to be in the right position for the Hohmann transfer to get you home again. And therefore, Mars missions are much more complicated than Moon missions. Not only are they much longer, they have to be at least something like 2 years long rather than 2 weeks long, because you have to wait for planetary alignment to work in your favor in order to use this transfer. Okay, that's how we get from Earth to Mars. What about getting around to other parts of the solar system? Well, back in the 60s, it was realized that in principle, with a big enough rocket engine, we can explore any part of the solar system we want to. We just have to make sure we've got enough fuel on board to burn those rocket motors for long enough to give us the delta V we need to accelerate to the point where we can then go visit the outer planets. But back in the 60s, it was realized that, hang on, why don't we actually use a slingshot? Why don't we use a flyby, or as NASA calls it, a gravity assist? If we fly past a big planet, well, almost any planet, we can do it in such a way that that planet gives us an extra boost. It can accelerate us. So we don't have to fire our rocket engines. We can get the planets to do the work. And it just so happens that in the 1970s, the outer planets, Jupiter, Saturn, Uranus, and Neptune, are in the right part of the solar system that we can slingshot our way from one to the other, the so-called Grand Tour. Hence, exploring the outer solar system can be carried out faster because you get a speed boost whenever you go past the planets on to the next planet. And if you're not firing your rocket engines to do that, you don't need extra fuel. If you don't need extra fuel, you can have more scientific payload. You can have a bigger spacecraft, more cameras, more scientific gear. So it's a win-win scenario. You get there faster and you can have a larger payload because you don't need to carry as much fuel. Fantastic idea. In a sense, the spacecraft is robbing some of the energy, or momentum if you prefer, of the planet. But it's not altogether clear how that works, because a physicist will tell you if a ball is rolling down a hill, let's imagine this is a hill and a valley and a hill, and like all good physicists, I'm going to ignore air resistance and I'm going to ignore friction. So this is an ideal system of a ball rolling down a hill. If a ball rolls down the hill, as it rolls down the hill, it goes faster. No surprise to everybody in the room, I'm sure. And it has a maximum speed when it's at the bottom of the valley. And once it's gone through the bottom of the valley, it'll start going up the other side of the hill, and it will start slowing down as it goes uphill. And if you started at rest and the second hill is the same height as the first hill, you'll end up at rest on the top of the second hill. But one of the basic physics ideas is about energy and how you're trading off. As you're falling, you're losing gravitational energy, but you're gaining kinetic energy, you're gaining speed. And the basic principle is that at any given height, doesn't matter what the height is, at any height, you'll have the same speed on the way in as on the way out. In other words, I could put that grey line anywhere, and at the same height, you'll have the same speed on the way in and the same speed on the way out. What is even less obvious, unless you happen to be a physics student, is that it doesn't actually matter what the shape of the hill is either. You can have a high gradient on one side and a very shallow gradient on the other side. Doesn't matter. If you draw a line at the same height, you'll go at the same speed because it's a conservation of energy argument. So if that's true, you start to think, well, how can falling towards Jupiter and then pulling away from Jupiter, how can that possibly give me a speed boost? Because surely what I gain on the way in, I lose on the way out. So how does a gravity assist actually work? If we think about coming in, let's say, to Jupiter, Jupiter's often used because A, it's the first one on the way out of the solar system, or at least it's the first big planet on the way out of the solar system. So let's think about flying past Jupiter. Max speed at the bottom of the valley, but in the case of falling into a gravity well, we're talking about the maximum flyby speed is when we're at our closest to Jupiter. So there's a certain speed on the way in and a certain speed on the way out. Let's imagine that we're dealing with distances that are so far away, it doesn't really make a lot of difference exactly what that path is. We're talking about when it's, let's say, for the sake of argument, a couple of million kilometers away, it's coming in with some speed. And when it's a couple of million kilometers away, going away from Jupiter, again, it should have the same outward speed. So that would imply gravity assists don't work because we've got the same speed coming in as going out. Here's the clever bit. It's the same speed coming in and the same speed going out as seen by Jupiter, because it's Jupiter's gravity well that we're going down and out again. So if we engineer it, bearing in mind that Jupiter is going around the sun and has its own velocity, if we come in broadside to Jupiter and leave in the same direction as Jupiter, it's the same speed relative to Jupiter, but Jupiter itself is moving. So we're now moving relative to an object which is moving quite fast in the direction we want to go. It's like being on a train and throwing a tennis ball. The tennis ball ends up traveling at a speed which is the speed of the train plus the speed of the tennis ball. So that's effectively what we're doing. By choosing the geometry appropriately, by not coming in the same direction of Jupiter, but leaving in the same direction as Jupiter, we gain Jupiter's speed. In effect, we are robbing it of some of its momentum. The difference can be quite considerable. For instance, if we get it right, we can come in relative to the sun at 10 kilometers a second, but we might leave at 25 kilometers a second. That's quite a speed boost, given that we don't have to burn any rocket fuel to gain that. We just have to make sure we fly in the right place. And NASA are good at sending things in the right place at the right time. And this is what they did with Pioneers 10 and 11 and Voyagers 1 and 2. So here's Pioneer 10 in the early 70s, leaving Earth, heading towards Jupiter. Look at what happens when it encounters Jupiter. Bam! A sudden increase in speed and a dogleg turn to the left because it approached Jupiter and then left Jupiter's environment in the same direction that Jupiter was traveling. Again, let's just run that simulation one more time. We've left Earth, we're heading towards Jupiter, we're slowing down, but as we head to Jupiter, bam, we get a sudden speed increase, and now we're heading off in a new direction. The same idea was carried out after Pioneer 10 with Pioneer 11. Once they had proved that that worked, they tried it again, but this time they headed towards Jupiter, got a speed boost, which sent the spacecraft right over to the other side of the solar system. Saturn is way over there, and the spacecraft was sent from one side of the solar system to another. The tick marks, by the way, just show where the spacecraft is relative to the plane of the solar system, the ecliptic, if you prefer. And once it passed Saturn, again, it got another kick and was effectively thrown out of the solar system. Both Pioneer 10 and Pioneer 11 are heading out of the solar system. Pioneer 10 in the direction of Aldebaran, Pioneer 11 in the direction of the center of the galaxy. The same idea was used again in Voyager. We leave Earth, we head towards Jupiter, and if we do it right, we get a kick to the left and a speed increase, which sends us flying on to Saturn. The main function of Voyager 1 when it got to Saturn was to have a close look at Titan. Titan is a very mysterious moon. It's quite a large moon, and it's got a very thick, hazy atmosphere that we can't look through very well, but we wanted Voyager 1 to get a close look. So Voyager 1 was tasked with get as close to Titan as you can. Don't worry about Saturn itself. Don't worry about trying to do a gravity assist. Just make sure you get close to Titan. So the timing there was crucial. That worked well. So Voyager 2 was a backup that also would have gone to Titan if Voyager 1 had failed. Voyager 1 got some nice images of Titan, which means Voyager 2 was free to have a gravity assist from Saturn. So that's what it did. It left Earth, got a gravity assist from Jupiter, and then Saturn, flew onto Uranus, took some images, and then flew onto Neptune. When it got to Neptune, they wanted to take some images of Triton, again, an interesting sounding moon, so they didn't attempt to have a gravity assist from Neptune. It was already going fast enough to leave the solar system, so there was no need. The tick marks tells you that it's taken a dive. The tick marks tell you it's now below the plane of the ecliptic. So Voyager 2 actually went over Neptune's North Pole in order to get a good view of Triton, and as it went over the pole, it effectively got deflected downwards. If we have a look at the speed of Voyager 2 as a function of time, as a function of distance, here's the speed relative to the Sun, vertically in kilometers per second, and horizontally we've got distance from the Sun in astronomical units. Of course, one astronomical unit way down here being Earth. So there's Earth, and Earth is going around the Sun quite fast, but as the spacecraft leaves Earth, it starts to slow down. But look at the kick you get from Jupiter, Saturn, Uranus, and Neptune. Notice that you get a hell of a kick even from Neptune, but you end up going slower than you started. Most of these steps result in an increase in speed. Except for Neptune, you accelerate on the way in, decelerate on the way out, and you end up going slower than you started because they weren't trying to get a gravity assist from Neptune. They were more interested in having a close look at one of its moons. And it doesn't matter if you want to leave the solar system, you don't need gravity assists from the outer planets Saturn, Uranus, and Neptune, because Jupiter is so big. Once you've got a gravity assist from Jupiter, you're already going fast enough to leave the solar system. If we look at escape velocity and plot that out, it's the blue line. So we're not going fast enough to leave the solar system initially, but as soon as we get that gravity assist from Jupiter, that huge spike there at about 5 AU, we're now going fast enough, and even though we slow down on the way to Saturn and we get another boost, we're still going fast enough to leave the solar system anyway. There's the escape velocity, and by the time we get to Uranus and Neptune, we have a velocity considerably higher than the velocity we need to leave the solar system. Using gravity assists to help us explore the outer solar system seems, well, sensible. If the planets are in the right place, then we can use Jupiter to help us get to Saturn and get us there faster, and we can use Saturn to help us get to Uranus and Neptune faster, and again, use less rocket fuel. So it seems almost intuitive that, yeah, it's a good idea to use gravity assist to go to the outer solar system. It's not so obvious that actually gravity assists are used all the time, even to get to the inner solar system. Bepi Colombo left Earth in 2018, and ever since then, it has been using gravity assist to get to Mercury. That seems a bit ridiculous. Mercury is really easy to get to. It's right next to the Sun. All we have to do is drop down a few orbits and we're there. But if we did that, we would be going way too fast. So it actually had a flyby of Earth, a flyby of Venus, another flyby of Venus, a flyby of Mercury, and it's doing flybys of Mercury and gravity assists from Mercury ever since. It hasn't gone into orbit around Mercury yet because for the last 7 years, or nearly 8 years, it has been going too fast. And it's using gravity assists to slow down, not by the one we saw before where we use the geometry to leave in the same direction as the planet. We use the geometry to leave the environment of the planet going in the opposite direction so that basically we lose some velocity. So a planet flyby or a gravity assist can be used to lose speed as well as gain speed, as long as we get the geometry of how we pass the planet, how we do the flyby. And a flyby, the bottom line is, it can be used to accelerate, it can be used to decelerate, but it doesn't really matter. What matters is, in both cases, you do not need to fire a rocket engine. You use the planet to help you speed up or help you slow down. So you don't need to use fuel. So that's why missions for the last few decades have all been using gravity assists, simply because you can get away with a larger payload for a smaller amount of fuel. And most of rocket science is about trying that trade-off. How do you get the biggest thing into space going where you want to go for the minimum amount of effort, for the minimum amount of fuel, the minimum mass of rocketry? Sometimes when you get to where you want to go, you do want to go into orbit and change your orbit. For instance, Cassini, when it got to Saturn, it changed its orbit. I can't remember exactly how often, but it was changing its orbit quite a few times over the length of time it was there. It arrived in 2004, finished in 2017. It crashed into Saturn in 2017. It made, I don't know how many orbital changes, but every time it changed its orbit, it had to use a little bit of fuel. And why did it keep changing its orbit? Well, because the astronomers, the astrophysicists, wanted either a close view of the planet, or a close view of the rings, or a close view of any of the hundreds of moons of Saturn, and they kept changing the orbit to get the best view of this or that or the other. But it takes fuel to do that. Eventually it ran out of fuel, and then they crashed it into Saturn. So that's how we get around the solar system. What about this idea of having parking places, Lagrange points? What are they all about? I return to this diagram because, again, I say it is key to what we're saying here. If we're close to the sun, things move fast. If we're further from the sun, things move more slowly. And we can ask ourselves, okay, under what circumstances can we change that situation? The arrows here show us that there's a strong pull towards the sun of the green planet, and there's a weaker pull towards the sun of the red planet. Greater the distance, the force is less. Hence a big arrow for green, a smaller arrow for the red. Is that always the case, we can ask ourselves? Well, we can't change the gravitational pull of the sun. That's determined by the mass of the sun. But what can we do about the pull on the red object here? We can arrange it so that the object in the red orbit feels an additional force. So we've got a certain pull of the green planet towards the sun. The red object, we can arrange it. If we now imagine that the green is Earth and the red is some object we're interested in orbiting, whether it be a spacecraft or something else. Let's assume that green is Earth, and so the green planet goes around the sun in precisely 1 year. The red orbit is further from the sun, so it has a period of more than 1 year. It would go around the sun on its own with a period of more than 1 year. But what if we can arrange it so that the red object is close enough to the Earth so that it's pulled by the sun and the Earth pulling in tandem? We can calculate that there is a red orbit, there is a distance that we can put an object in, as shown by that diagram, such that it's pulled towards the sun, the yellow arrow, and it's pulled towards the Earth, the green arrow. Both of those arrows in the same direction, so they add together. The result is more gravitational force. The result is, instead of taking more than a year to go around the sun, it takes a year to go around the sun. That means the red object goes around the sun in sync with the Earth. So they go round together. The red object is always pulled towards the sun and the Earth because they both have a period of 1 year. Green is pulled by the sun, red is pulled by the sun and the Earth. And so they go round in sync. Let's just run that again. The red object is always in line with the sun and the Earth. Sun, Earth, red object are always in a straight line. The red object is hovering above midnight. It's hovering above the midnight side of the Earth. That is precisely what Lagrange 2 is all about. If we just take away the unnecessary bits and pieces, Lagrange 2 is this place such that the pull of the sun and the pull of the earth combine to give you a period of 1 year. So L2 basically stays fixed relative to the sun and the earth. It's always a straight line from the sun to the earth to L2. The scale is way off. I haven't attempted to draw this diagram to scale because the distance from the earth to the sun is 1 astronomical unit, and the distance from L2 to the earth is something like 1% of that, about 0.01 astronomical units. So quite definitely not to scale. The idea is essentially the same. Conceptually, it's exactly the same for L1, which is a point inside the orbit of the Earth. Normally, objects closer to the sun will go round faster, but we can find a point so that the pull of the sun and the pull of the Earth are now in opposite directions. So if they're pulling in opposite directions, the pull on that particular point is less. And so instead of going round in less than a year, it takes 1 year. And so L1, again, goes round the sun at the same rate that the Earth does, 1 revolution in 1 year. Again, I haven't drawn it to scale. 1 astronomical unit from Earth to the sun. L1 is approximately the same distance that L2 is. It's about 0.01 astronomical units from the Earth. L1 is a great place if you wanted to study the sun. In another year or two, the NEO-Surveyor spacecraft is going to be placed at L1 because it's going to be looking out for any objects coming out from behind the sun that we would otherwise miss. It's very easy to find objects like comets and asteroids on the night side, but it's much more difficult to find them if they're coming from anywhere close to the sun. So NEO-Surveyor will be a spacecraft, a new space telescope, which will be sitting at L1, checking for any asteroids that peep around the sun to give us a little bit of a heads up before they smash into the Earth. Maybe we won't be able to do anything about it, but at least we'll get a little bit of advance notice. We can calculate where these Lagrange points are, because all of the gravity we're talking about, we don't need to worry about any Einstein general relativity. This is all just Newtonian mechanics, effectively, classical mechanics. We know that the force between two bodies, if we have body A and body B, and we know their masses, we can calculate the gravitational forces between them. Depends on the masses, and it depends on the square of the distance between them. So we can use that to calculate where L1 and L2 are. And the maths is pretty straightforward. All we have to do is to solve that equation. M's are the masses involved, R are the distances. Just solve for R. Simple. I guess we can. Do you want me to just wait a few seconds while you do that in your heads? No? Okay. Yeah, I know I said it's not that hard if you just skip the maths. Yeah, okay, I did say that, didn't I? Okay, so let's just skip the maths. The point is, you can write down the equations according to Newton. Forces are just given by mass, and distance squared, and you can work out where do I need to be to give me a period of 1 year for an object in the solar system, and it turns out you can be at L1 or L2. It's not so obvious, but actually L4 and L5 satisfy the criterion as well. That's by no means obvious, because when we're talking about L1 and L2, the forces of Sun and Earth are in the same direction, or possibly in the opposite directions, but they're easy to work out. It's not so obvious that if you're sitting at L5, the sun is pulling you one way and Earth is pulling you, well, a completely different way, 60 degrees different. And it's by no means obvious that when you work out what's going on, when sun is pulling you that way and Earth is pulling you that way, lo and behold, you find that you're on a static point, which again is going around the sun at precisely 1 revolution in 1 year. It's perhaps a little more obvious that L3 works, but L4 and L5 does take a bit of geometry and a bit of trigonometry to work out what's actually going on. But this was worked out by clever mathematicians a long time ago. Euler and Lagrange worked this out. Euler worked it out first, but Lagrange came along and stamped his name on it, like many people often do. And that's why we place spacecraft at L2. It's a nice parking spot. On this side, of course, we'd have the glare of the sun. On this side, well, we can have a sun shield, whether it be for Gaia. I think you've heard about Gaia as of a month ago. We can have Gaia with a sun shield, or the James Webb Space Telescope with its sun shield. And the sun shield can be arranged such that it blocks all the light from the sun and the Earth and the moon simultaneously. Of course, at L1, we've got the sun on one side and the earth on another side, so we can't shield them at the same time. But if you park yourself at L2, then you can shield yourself from anything on the sun side, and you're left with a beautiful dark sky, as it were, on the other side there. Now, L2 is actually in Earth's shadow. L2 is about 1 million miles above midnight. That's 4 times further than the moon. And remember, the Earth is about 4 times bigger than the moon. So remember, the moon's shadow just touches the Earth during a total eclipse of the sun. And if Earth is 4 times bigger and L2 is 4 times further away, well, that means basically that the Earth's shadow just about reaches L2. So if you were to sit at L2, you would effectively see an annular eclipse as sunlight just creeps through the Earth's atmosphere. So it's not a good idea if you've got solar panels to sit in the shadow of the Earth. And also, we'd like to put more than one spacecraft there. We'd like to put Gaia and James Webb and a few other things there. So you don't actually sit the spacecraft at L2, you actually do a little so-called halo orbit, an orbit that in this case is out of the screen. We're looking at the plane of the Earth's orbit on the screen, but a halo orbit is coming out of the screen. That's why it's called a halo orbit. If a spacecraft moves away from L2, it gets pulled back by the Earth. In other words, in this particular screen, if we were a little bit high, it gets pulled down. If we're a little bit low, it gets pulled up. The Earth will pull it towards that particular Sun-Earth L2 line. But if a spacecraft drifts towards the Earth or away from the Earth, it will keep drifting towards the Earth, or it'll keep drifting away from the Earth. In other words, that's a sort of unstable situation, like a ball rolling off a hilltop. And we can get an idea of what's going on at these Lagrange points by using this rather colourful looking donut. It's a way of trying to visualize what's going on at the Lagrange points. We're not going to work out all of the physics, we're not going to do all of the maths, but this is effectively saying, well, what are the forces on an object that are sitting anywhere in the solar system? We can think of it in terms of, let's imagine these contours on this donut are height, and we're thinking about whether a ball wants to roll downhill, and then we can work out which way an object will want to move. We're solving Newton's equations of motion, but we're then visualizing the results by putting them on this particular donut. So imagine that the contours represent height, so red are high contours and blue are low contours. And we're trying to work out whether or not, if we placed a ball on this surface, whether it would roll downhill and which direction would that be in. So let's have a close look at L2. We're not going to worry at the moment about L4, 5 or L3 or indeed L1. We're going to look just at L2. So let's just zoom into that bit so we can see it a little more clearly. Red is high, blue is low, and we're interested at what happens in the vicinity of L2 there. So if we draw downhill, downhill is going from red to blue, which is in this direction towards L2 for the top arrow and the bottom arrow. But if we look at the left arrow and the right arrow, they are pointing away from L2. So L2 is not a hilltop. It is not a point where you always go downhill when you move away from this point. L2 is not the top of a hill. Also, L2 is not in the bottom of a well. Again, all 4 arrows, or all arrows in principle, are not pointing towards L2. L2 is actually a saddle point. Mathematicians call it a saddle point because if you are sitting at that saddle point, 2 directions takes you down and 2 directions take you up. Mathematicians call it a saddle point. Everybody else calls it a Pringle. That's why we had Pringles on the table at the back there. So, the James Webb Space Telescope is sitting on a Pringle. If that's the only take-home message from this evening, that's all you need to take away from this particular talk. So again, there's James Webb at L2 in a halo orbit, not actually at L2, but orbiting around L2. And because the Earth will pull it back if it the Earth will pull it back if it drifts this way or that way, but if it drifts towards Earth, it'll need a nudge back to L2. If it were to drift away from L2 in this direction to the right, how do we get it back again? We haven't got any jets on this side. We haven't got any rocket motors. Remember, the right-hand side of the James Webb, as you're looking at it, is the cold side. The sun shield is keeping all of the sun's radiation and the Earth's radiation and the moon's radiation. So the left-hand side of James Webb is getting hot, but the right-hand side is only a few Kelvin above absolute zero. We do not want any rocket motors or jets on the right-hand side, either warming up stuff or giving us any horrible jet residue on the mirrors, for instance. So if James Webb drifted too far from the Earth, it wouldn't actually be possible to nudge it back again. So the rocket engineers, the rocket scientists, tried to place it just left of L2, such that it would slowly drift towards Earth, and every once in a while, roughly every few months, it would need a nudge to get it back close to L2. And they wanted to be absolutely sure they didn't nudge it too far. Nudge it towards L2, let it drift towards Earth. Nudge it back again a few months later, let it drift towards Earth. So it needs a little bit of station keeping. It needs a little bit of fuel. But they were so accurate when they placed James Webb Space Telescope at L2 in the first place, they saved so much fuel, it effectively extended the life of James Webb from 5 years to hopefully 10, 15, or even more years, because they got plenty of fuel in reserve to make these station-keeping nudges. Yeah, rocket science is tricky because some orbits are really weird. For instance, there are things called horseshoe orbits. Yes, there are objects that move in ways like this. Let me put the arrows in. You look at that and you think that's ridiculous. Nothing ever moves in an orbit like that. But if you look at it very closely, it still obeys the rules. When closer to the sun, it goes faster than the Earth. When closer to the sun, the object is going faster than the Earth. The Earth is going around the sun anti-clockwise. We're looking at it above the North Pole. So the object is catching up the Earth. As it approaches Earth, Earth pulls on it and it ends up further from the sun. What happens when it's further from the sun? When it's further than the sun, it goes round the sun more slowly than the Earth. And so it appears to go and lag behind the Earth. Eventually, it gets close to the Earth gives it a little pull, and it ends up closer to the sun, in which case it goes faster than the Earth, and then slower than the Earth, and then faster than the Earth, and then slower than the Earth. And it goes round these horseshoe orbits. As far as we know, there are not many objects orbiting the sun that follow these, but there are horseshoe orbits around other planets. We see some moons around other planets that are in horseshoe orbits. So these things do exist. They're not simply mathematical curiosities. Some objects do move in the solar system according to this sort of pattern. And possibly the weirdest orbits of all, remember, an orbit is not necessarily a closed loop, it's not necessarily a circuit or an ellipse. An orbit is simply a path controlled only by gravity. Here's a simulation of a rather hypothetical situation. What if we started with 3 masses, and each of them is attracting each of the other 2, and we are going to place them here, let them go, and simply let gravity do its stuff? What is going to happen? Well, green is obviously going to be pulled to the left, red is obviously going to be pulled to the right, and blue, when you think about it, if it's being pulled towards the other 2, presumably blue is going to head downwards. But what they actually do is very, very non-intuitive. We put them there, we let them go, and gravity does this. And then they stop and they come backwards again and follow exactly the same paths. And they would just do that back and forth and back and forth. Green would just do that back and forth, back and forth. Red would follow that M back and forth. Blue would follow that loop. They are obeying the laws of gravity. It is very unlikely we'll ever see a triple star do that, because the only way we can get that to work is to start with 3 stars, exactly the right mass, exactly the right position, not moving at all, and then let them go. And stars aren't born that way. So it'll never actually happen, but mathematically that is obeying all the rules we understand for how objects move under the influence of gravity. And don't get me started on black holes, because black holes, the space around a black hole is so distorted that the idea of Kepler orbits and Newtonian conic sections, they just go out the window completely. We have to rely on Einstein's general relativity if we want to understand how objects move close to a black hole. So why is rocket science considered to be so hard? Why do we keep saying, well, it's rocket science, it's obviously very, very difficult? Well, yes, there are clearly some objects moving in the solar system in orbits that are, at first sight, certainly not intuitive. Even at second sight or third sight, they still don't look intuitive. Even when you solve the equations, it takes some convincing that they are actually doing what you would expect them to do. And yes, calculating how you are going to put James Webb Space Telescope at L2 with such exquisite precision that you can actually save fuel to extend its life from a few years to possibly a few decades. Getting it to L2 with such accuracy was pretty amazing. So that is true. But the underlying idea is simple enough. The underlying idea is stronger gravitational pull gives faster motion. In other words, Earth goes around the sun faster than Mars. Everything else, well, the rest is just maths. After all, it's not rocket science. Thank you.